Hello everyone, today you're going to go over open and closed sets. But before we can understand those, we have to go over a few concepts beforehand. One of those concepts being a neighborhood. So what is a neighborhood? Well, M is a neighborhood of small x if x is a member of some big set X, and small x is a member of the neighborhood M, and there exists some epsilon that's greater than 0, such that the ball around X is contained in the neighborhood M. So what do I mean by this? Well, so we have some big set X, okay, big X, and I have some point small x, okay? Then I have another set. Let's call this set M. Alright? So this M set, M is of course like the set of like all these points you see in here and the boundary. So M is a neighborhood of this small x, because this small x is contained within this big X, correct? And X is also contained in this M, and there exists some open ball around X that is contained in M. That's all it means, right? So this point Q would, like, M would be a neighborhood of this point Q, right? Since there is a open ball around Q that is contained in M. How about this point I don't know, J? Is M a neighborhood of J? Well, no, right? Because there doesn't exist an open ball around J that is contained in M. Now you can try making this one, but it's not contained in M. Even this giant ball over here, some of it is in M, but all of it isn't contained in M. So M is not a neighborhood of J. Okay. Now what about points on the boundary? Say I have some point, let's call this a W or a omega. So is M a neighborhood of omega? Well, the answer would be no, right? Because like any ball I make around omega, it wouldn't actually like the ball wouldn't be contained in M, because no matter how small I make the ball, it wouldn't be contained in M. So, because remember that a ball is defined this way, right? So the ball will always contain the center, but it always has to be like contain more than the center, right? Since like for any arbitrarily small epsilon you have, you are going to have other points that are still in the ball set, and epsilon can't be 0, right? So the boundary of M, all the points on the boundary of M cannot be a neighborhood of those points. Okay, so that's all it means. So now let's define the interior point. Well, the interior point is defined as x being an interior point of big X, a small x has a neighborhood of M where M is contained in big X. This is alluding to the definition that I gave earlier for a neighborhood. So basically, in this case, X would be an interior point of big X, since there is some neighborhood around X that is contained in big X. So M is a neighborhood of X, and X is an interior point of big X, since there is a neighborhood around X that's in big X. That's all it means. And now let's define the environment. The environment is defined as a set X that has a point X which has a neighborhood of M where M is in X. X is an environment of X, and X is the environment of small x, and small x is an interior of big X. Okay? This is, like, again, similar to the ones I gave earlier. We have some big X, we have some small x, we have some neighborhood M, right? So here M would be the neighborhood, small x would be the interior point, and X would just be the environment. Okay, that's all it's saying, like behind all that jargon. Um, so yeah, that's what it's saying. Now let's talk about the interior set. So interior set is basically defined as a set of all interior points, essentially. So if I have some set big X, all the interior points of big X would be the interior set, right? And all of these points, as you can see, would be in the interior set, since there exists the ball that's contained in some neighborhood that's contained in X. So now let's define the open set. The open set is defined as a set of points U, where for all U is in big U, there exists some epsilon, such that the ball around U is contained in big U. So what does this mean? Well, so you have some set that looks like this, okay? Ultimately, it's a set of all points U, right? So like X, Y, Z, A, B, C, right? Where we can form some ball, right? So we can form some ball around those points. With those points, with those balls, still being inside of U. So it's basically like really, it's just the interior set, pretty much. I'm not really sure like what's the big difference between those, but like it's basically like an element. I mean, it's some set, right, where all the points are interior points, right? So I guess you could say like it's some set where all of its constituents are the interior set, pretty much. I guess you could say it like that. So yeah, that's what it is. So as you can see, a point on the boundary, it's called this point I don't know, gamma, is not included in the open set, right? Because we cannot form any ball here that isn't completely contained in the set, right? Like this ball over here isn't, like, no matter how small I get the ball, it won't be in the set, and I can't have a ball that contains only the point, right? Since like for any arbitrary epsilon, there will always be some other point, right? Or space isn't like discrete or anything; it's continuous, right? I know I can get as close as I want to the boundary, right? Because I can have some point, like let's call this point z tilde. Like there's still some like super small, really small ball around z that is not that does not go to the boundary. But the boundary itself isn't in the set, right? Since balls around points in the boundary are completely contained in the entire set. So this is pretty much just a generalization of open balls. Remember that open balls, like, they look like this in like the R2 space. Well, now open sets are like pretty much like just like weird lumpy balls. Like the union of two open balls would be an open set, pretty much. An open set is just like any like weird shape that doesn't include its boundary. So it's like a generalization of that open ball. An open ball would be an open set trivially, since any points inside the open ball would be contained in that open ball. I believe that we can also define open sets in terms of neighborhoods. Since like if there is an open ball around X that is in the set, of course then there is a neighborhood around X. You could define it where it's just that there's a neighborhood. In fact, the interior point is defined as a neighborhood. So like yeah, this definition pretty much includes neighborhoods by default. So what is a closed set, you ask? Well, a closed set is pretty much the opposite of an open set. In other words, it's defined as a set of points where x is in U, where x is not in O, where O is the open set. Okay, so basically for all of these open balls I had, like they existed in like some, sorry, in all these open sets, like they existed in like some like space, big U. Should have noted that, right? So the closed set is a set of points, x, where x is in U, big U, but x is not in O, where O is the open set. So it's pretty much saying that it's all the points that aren't in the open set. So if I have some open set, so sorry, I should just draw U first. So like here's some, so here's U doesn't have to be a rectangle. It could be anything really, but I just like using it as a rectangle. So yeah, U would be the environment, by the way. Let's say I have some open set. We can agree that this set is open until it's open set O, right? Since like any point inside has an open ball that's contained in O. Okay. Now the closed set will just be all the points that are in U but are not in O. Okay, so pretty much every point other than the O, like it's like literally everything except O that are in this set U. Right? And this is this is a closed set, and it actually generalizes the closed ball, since the closed ball is just everything inside of it except everything inside of it, including the boundary. Well, now here you have like here it includes the boundary, right? And it includes the boundary. The boundary isn't in the open set, so it would actually include that boundary, right? But just not anything like inside the boundary. So this is to be honest here, this is really like a generalization of the sphere in a way, but this is what a closed set is. Now, say I had some U here, okay, and I had some set that looks like this, okay, and it includes a boundary. Let's call this J. Yeah, and J includes like all the points inside of it as well. Now J would be a closed set, right? Since a closed set is just defined as like a set of points where x is in U, where x is not is not in an open set, pretty much. So we can verify that this is a closed this is a closed set, since all the points inside of J aren't in the open set, right? Because like everything outside of here is an open set. What would be an open set, right? Since we could take like any ball here, sorry, you could take any point, make some sphere, right? And it doesn't include the boundary of J, right? It doesn't include J's boundary anymore, right? Since boundary of J is in the closed set. So yeah, we can take we can get as close to J as we actually want, right? But we can't touch that boundary there. So that would be an open set. So we probably could have defined this in a bit of a better way, since like we could have points in J. Sorry, we could have points in J that are in the open set if we make this like some open set, right? So it's really just defined as like so closed set is really defined as like the complement of the open set. Just so you have some set, right? You just have some set. If everything that is not that in that set is open, then that set is closed. And if I have some open set, and everything that is not in the open set, all the points that are not in the open set will be closed, right? So closeness is the complement of the open set. So yeah, that's all what it means. So I hope you guys understand what open and closed sets are now. So yeah, if you have any suggestions for me, please comment that down below. And if you like this video, please consider sharing it. It really helps. So yeah, have an